Okay, let's get started. So we're lucky to have Nicolas Loizou as our speaker today. So Nicolas is an assistant professor in the Department of Applied Mathematics and Statistics at Johns Hopkins University, where he leads the Optimization and Machine Learning Lab. He was a postdoc research fellow at Mila, and he completed his PhD in the University of Edinburgh School of Mathematics. Before that, he received his undergraduate degree in mathematics from the National and Kapodistrian University of Athens and obtained his master's degree from Imperial College London. His research interests include optimization, machine learning, distributed and decentralized algorithms, game theory, federated learning. He received OR Society's Doctoral Award, COPE Best Paper Award, and Cisco Research Award. And today he's going to tell us about next-generation adaptive optimization algorithms.
Thank you very much, Murad, for the great introduction. And that's a seminar that we are just 10 in the room and another few on the Zoom. So feel free to interrupt at any point and let me know if something is unclear. You can see I have 46 slides. There is no reason to cover all of them. So if something is unclear, let me know and we can dive into the details, okay? So as far as I know, I will speak about adaptive optimization, by the way, some Polyak type algorithms that we developed the last few years, how they belong in the literature of adaptive methods, what are their benefits, and how can compare with methods like AdaGrad, Adam, the more popular in machine learning and deep learning theory optimization algorithms. So I know that some of you might have background in optimization, some in machine learning. So I will spend the first few slides just to motivate why we need stochastic optimization algorithms or stochastic training methods. This will be quite fast, but the main part of the talk will be section 2 and 3, where I will explain what is a stochastic Polyak step size for SGD. And then I will dive on a decreasing version of it and how all of them can interplay with momentum, the one that we use in all optimization algorithms for generalized betting. Okay. So as we know, optimization problems are everywhere. We try to minimize a function f of x under specific constraints. These problems appear in finance, in statistics, in engineering, and in many problems in machine learning and data science, like visual object recognition, speech recognition and natural language processing, personalized recommendation, image segmentation, and of course, the training of deep neural networks, and many more. So these are the problems that my group is interested in. We try to design algorithms for solving these kind of problems, and we try to do that as fast and as reliable as possible. And some just more examples of where optimization problems appear. We can have them in personal recommendation, in Amazon, Netflix, and YouTube, in speech recognition, like Hi Siri and Google Assistant, and of course in action and object recognition in images, and lately in distributed and federated learning, where we try to preserve the privacy of each client. Okay. And the problem that we will focus today is mostly supervised machine learning. Some of the ideas can extend to more general settings, but that will be the setting that we will focus on, where we have n observations of data, where AI is the input feature vector, and BI is its label. And our goal is to find the parameter X that characterizes the model better, that fits the data better. And we have this empirical risk minimization, which is a minimization of a function f of x, which itself is an average of fi functions. And here, the setting that we're interested in is when the parameter n, the number of fi components, and the dimension d are huge. In that scenarios, you cannot run methods like gradient descent or Newton method because they are extremely expensive. And this is where stochastic optimization methods come in place. And this is what everybody runs in practice, okay, when you have extreme scale scenarios. And just to give you a brief overview of what we call gradient descent and stochastic gradient descent, in case that you're not familiar with, I think in the room, most likely all of you are. So if we have a minimization of a function f, which is an average of fi's, then you can see that the deterministic gradient descent takes the gradient evaluated in each step, which means that as the n increases, you increase the iteration cost by n. Okay, so if your n is huge, then the evaluation of gradient will be huge as well, and very expensive. While in the stochastic gradient descent, in the most simple format, what we do, we sample one of these FIs, using either a uniform or of any other distribution, and by sampling, we selecting it, and this is an unbiased estimator of the full gradient. And we move towards the negative direction of this unbiased estimator. And the most important thing that we should understand of why stochastic gradient descent should prefer over gradient descent is in the scenarios where we have low accuracy time situations. So if you don't care about high accuracy solution, like in most of deep learning scenarios, we are enough of finding a low accuracy point, a low accuracy stationary point, or if we have restricted time situations, we have a limited time to produce the outcome that we want, then using stochastic method is a preferred choice because gradient descent is so slow, it takes so much time, okay? And we have some papers in this direction, analysis of AGD in general settings, non-convex deep neural networks, convex, strongly convex, and goes on. The last few years, I will not focus on this, but I just pointed here in case that you are interested in to check them out later, or we can discuss after the seminar. Now, any questions about the setting? Is that clear? Everybody knows what SGD is? Okay, very good. So let us go into the adaptive setting now and some terminology. We will focus in this talk on the minimization of a function f of x, which, as I mentioned before, can be expressed as an average of n component functions fi. Here, x corresponds to the model parameters, n is the number of training data, and fi represents the loss on the training point I. With capital X star, we will denote the set of optimum points. F star is the minimum value of f, and for each I, we will denote with fi star the infimum of function fi. Okay? And throughout this talk, we will assume that the f and fi's are smooth. Most of the results that I will present can easily extend it to the non-smooth case, but for simplicity, everything will be smooth. And based on the model understanding, we can have strongly convex, convex, or non-convex problems. And I will focus on a few papers. I will take some parts of each one of them. So I will start with the first paper from 3 years ago, just to show you the background on the stochastic Polyak step size for AGD. Then I will move to the decreasing version of it. And I will cover later, and that will be the focus at the end of the talk, of how this can interpret with a momentum parameter and how you can have efficient momentum algorithms that using the Polyak step size. This is a paper from last month. This is from a few months ago. So the progress in stochastic Polyak step size is quite interesting this time of the last 2 years, I would say. Many people are interested to explore this direction because the behavior is very good, and we try to understand why, okay? So as I mentioned, AGD, in every step, you select an unbiased estimator and you move towards a negative direction. The most important parameter that requires tuning is this gamma k, the step size of the method. You can have different choices. You can have constant step size that you keep fixed throughout the algorithm and you tune it well in advance. You can have decreasing step size selection, that then the step size goes to 0 as the algorithm progresses. And you can have adaptive methods as well that adjust the step size on the fly. So, and adaptive methods, the last few years are the go-to algorithms for tuning the step size in AGD, especially for deep neural networks. In the classical analysis now, the convergence guarantees of the method, the step size typically depends on smoothness or mu strong convexity. That parameters that typically they are not available to us for all problems. So what practitioners do Either they go and they do long trial and error procedures to find what is the parameter. They do tuning that might take a few days to understand what is the parameters for each specific application, or we can design parameter-free or adaptive methods for solving these problems that they do not require any tuning. You know that it will work. It might be a bit slower, but the benefits of avoiding the tuning is so huge that you don't care if it's a bit slower. And there is a rich literature on adaptive methods. You might have heard the autograd and adaptive methods, but in several scenarios, especially in stochastic non-convex regime, these methods might fail to converge an optimal solution. And you can come with counterexamples that this might be the case. So, and what we suggest is use these SPS ideas that exactly what the theory predicts, exactly what is the form of the SPS stochastic Polyak step size is exactly what you run. It's not like Adam that you can have a momentum and a step size that is not related to what you actually run in practice. Okay. And just briefly, what we will cover, we will explain what is a stochastic Polyak step size. It's an extension of the classical Polyak step size from the 80s that proposed by Polyak himself for the deterministic method. Now we extend it to the stochastic regime. We will explain how you can obtain convergence guarantees for AGD using this step size. Important for some people that they care about the theoretical guarantees and how important are some assumptions. We don't require to have bounded variance or bounded gradients. These are very strong. We don't need such assumptions to guarantee convergence. And the methods that we will explain are very beneficial in over-parameterized models when you have an interpolation condition satisfied. And this is most of the case these years for many deep neural networks as well. And I will show some experiments on deep neural networks and some convex optimization problems. Now, let us dive into the details. And this is where we will focus some time because it's important to understand exactly what is the Polyak step size. So if we have the gradient descent method, this update rule here, then as I explained before, there are many ways of tuning the gamma k, the step size. So what Polyak suggested 40 years ago is that you can select the step size to be the ratio of the function suboptimality over the norm of the gradient evaluated at xk. So here you can see that the step size itself depends on the optimum function value, this f star. So how you can know the value at the optimum solution well in advance in order to tune it and have a valid step size. And what Polyak suggested is that for many problems in optimization, this is known and is equal to 0. If you have consistent linear systems, least squares in machine learning setting, if you have to find a point at the intersection of convex sets, all of them have f of star equal to 0. And this means that the step size itself is just the function value evaluated at xk over the norm of the gradient. And that's it. That's what Polyak proposed for the deterministic gradient descent and comes with convergence guarantees. So you don't need to tune anything. You don't need to have anything known well in advance. Just running it, you have convergence. Okay? The important thing is to know this f star, but as I mentioned in several problems, is equal to 0. You don't need to know what is your x star. You just want to know what is the function value for the x star. Okay? And what we are suggesting, and this is our proposal, is to extend these ideas to the stochastic setting. And it's as simple as it gets. You can see in this AGD, we sample one of the FIs, and once you sample it, you use it in the Polyak step size itself. And what is a Polyak step size? Is again, what it was the deterministic version, but now in the stochastic regime. We take the function suboptimality over the norm of the gradient. And note that this step size does not depend on L smoothness, does not depend on mu, does not depend on any quantities of the problem. And what I claim is that the same step size can work for convex, strongly convex, non-convex, without any change. It's the same step size, and you have convergence guarantees to a stationary point.
And I will explain what this means. Because the stationary point here, we have convergence to a neighborhood, but I will explain what scenarios the neighborhood disappears. So you can see here that, as I mentioned, the step sizes, they do not require the L smoothness. They do not require the mu. But on the other side, they require this knowledge here. How is it possible to know the infimum of each Fi before you run the method? That's the main question that one can ask. And C is said theoretically can be equal to half when you have strongly convex problems. When you have convex, can be equal to 1. So it's not a parameter that requires tuning as far as you know the setting that you are in. And this gamma b, as I will explain, is a bound that keeps the SPS small and it does not explode. It does not, we don't need to make any assumptions on the gamma b. It can be 10, 100, 1 million, and still have convergence. But these affect the neighborhood of convergence that you will have. And I will explain in theory what this means. Now, the most important part is this thing. Okay, you remove the L, you remove the mu. But what is the point of having the effort star? How is that known? And what we argue is that for standard unregularized surrogate losses, let's take square loss, logistic loss, exponential loss, Hitch loss, all of them that are very popular in machine learning, all of them have the same characteristic. Fi star is equal to 0 for each of I. If you plot the Fis, all of them have infimum equal to 0. So this means that if we go back, the step size itself, what we are suggesting is just once you select and sample the Fi, your mini batch, what you will do, use the function of this mini batch in the numerator and the norm of the gradient of this mini batch to the denominator. And that's the step size that we are suggesting that it will work out. Okay. So let me stop here. Are any questions about the format? Is clear? Yeah.
Just to clarify, so Fi is the function of the parameters given fixed mini batch of index I. Okay.
So in every step of AGD, you sample your mini batch. This mini batch is what we represent here as the number of Fi. Now, once you have the mini batch, you know exactly what Fis you use. The sum of these Fis is your mini batch here in the function value. And then once you have the gradient anyway, you take the norm of this gradient squared for your denominator.
Yeah.
And because in many examples, this Fi star is equal to 0, that's the step size adaptive. Because this does not reduce, does not increase, it fluctuates based on the xk that you have and the mini batch selection. Any other question on this?
Does the analysis you'll present work in continuous time?
I have no idea. You mean with not discrete time, what you will run, but
yeah, like some continuous time
yes,
analog of what is going on.
Yes, so I don't think that anybody did that. But I'm not sure. What is the benefit of going to the continuous time?
I mean, I would probably connect it to like gradient flows in the space of probability distribution and then apply it to sampling, and then you would get parameter-free sampling algorithms, which does not exist. So
that's interesting. So yes, the gradient flow part, I don't think that anybody makes such connections here. Okay. Yes.
In the deterministic case, C is equal to 1. So the new value of C for the stochastic case is that.
Even in the deterministic case, so if you have strongly convex problems, C is this. And if you have convex problems, C is this. In the deterministic case as well. So we recover exactly what the deterministic Polyak step size has.
Okay, thanks.
Okay. Any questions before I move on? Okay. And I will not dive into a lot of the theory part, but the important thing is that we make assumptions on the function. We run this SPS max with a positive gamma b. And what we notice is that for the same quantities that the standard AGD converge, we have exactly convergence for SPS max. And let me explain what this means. So these are the quantities, the measure of convergence that goes down. When you have strongly convex, then you have on the iterates. That's the standard thing. When you have convex, this is the Cesaro average. When you have a Polyak-Loizou condition, this is the functions of optimality. And when you have non-convex problems, this is the norm of the gradient. It's a standard quantity that needs to go down in order to guarantee convergence either to a stationary point or to a minimum. And what we can guarantee is for strongly convex and PL problems, we can have a linear convergence. And for convex and non-convex, sublinear convergence. And all of them are related to a neighborhood that I will explain in the next slide what this means. That is proportional to the gamma B and to a sigma square, where the sigma square is the optimal objective difference. So at the optimum point, how far is your actual function value from the expectation of the individual Fi stars? Okay. Note that this is 0 by default when you have over-parameterized models. So when you have over-parameterized models, then each of the Fi share the same minimum with the F. And in that scenario, the sigma disappears, becomes 0, and you don't have convergence to a neighborhood anymore. Okay? And I will explain what this means in the next slide, if you care about theory. If you don't care so much about theory, I will just skim through the results and go to the practical applications of the SPS. So just to give you an example, here we run it, the classical minibash AGD, and we select the minibash SK, and now we select the step size to be this SPS max. As I mentioned before, the FSK minus FS star, and then we divide by the gradient. And the gamma B is a constant parameter that we don't care about. It's just is there to not have the step size explode. And here for strongly convex problems, we can guarantee linear convergence to a neighborhood of the solution. And this neighborhood depends on the sigma B that I mentioned before, and to the gamma B, this upper bound that you have there. Okay? So what this says is that the convergence is to a neighborhood of the solution, a ball around the solution. And it's very similar to when you run constant step size AGD. That's exactly the same result. You cannot find the exact X star, but you converge close to the solution of the problem. Okay? And the same goes with the convex case and non-convex scenarios. But instead of linear, we have this 1/k convergence plus a neighborhood of the solution. Okay? If the sigma B is equal to 0, for example, in the interpolation regime, then in convex and non-convex problems, you can guarantee 1/k convergence. Okay? Before I move to experiments, is that clear, at least from a bird's eye view, what is the main contribution here? And what is the format of the Polyak step size? That's the important part.
Can you please define what do you mean by interpolation regime?
Yes, so I gave the definition here. So the over-parameterized models. So here it's not fully accurate, but the connection is that if you have an over-parameterized model, then the interpolation condition is satisfied. This is a connection. So when you have over-parameterized model, then each of these Fi's that you have, your minibash, share the same minimum with the original function. So you have an X star, which is the minimum of your problem or your stationary point. And this X star is the same, is the one that minimizes each one of the Fi's, each one of your minibash.
I see. So it's like in the case of infinite width neural networks, then everything becomes convex, then they share the same.
Yes. So that's the definition. Over-parameterized model, typically at least, people claim that if you have over-parameterized, the interpolation condition is satisfied. And this is what we call interpolation, is that each of I or a minibash share the same X star. And yeah.
Question about the neighborhood. So the neighborhood means like an error threshold of how close you're gonna get to the optimal solution.
Yes, it's a ball around the solution that you can guarantee you reach it but you don't guarantee that you find the exact solution. This is exactly the same with a constant step size AGD. If you run a constant step size AGD, you converge, you can guarantee conversions to a ball around the solution, but not to the X star. Except if you use decreasing step sizes, that it will be the next part of this talk as well.
Okay, thank you.
And just to show you some examples, when we have logistic regression problem, here I have the regularized version. We can run it and we can see that as the gamma B increases, you can reach to exactly larger neighborhood, what I described before. So for example, here the green line, you can see that all of them converge with the same pace, but they stop to a ball larger than the exact solution. You can have larger ball or larger neighborhood as gamma B increases. The important thing that you should take from this is that a highly tuned AGD that you don't know how you will tune it. You can have it with 10 to the minus 3, 10 to the minus 5, 10 to the minus 4, whatever step size you use. You converge at the same exact pace as the Polyak step size that doesn't require tuning. That's the selling point here. And if we go beyond the convex case, we have some examples on basic deep neural networks, CIFAR 10 and CIFAR 100, ResNet 34. People already extend them in many other settings, but just for illustration purposes, I have this here from the original paper. In terms of train loss, you can see that our method is the orange one, is the red one. And you can see in terms of train loss, it goes very fast down. And in terms of generalization, performance is very competitive to methods like Adam and this SLS or look ahead and all of these algorithms that they use. Of course, for generalization, we don't have any guarantees. We don't focus on this. We just plot the generalization to see how it looks like. And that's the performance of the method. Okay. And here we plot the step size as well. And what is very interesting is that the step size itself has a warm-up phase that at the moment, we don't have any theory for this. We don't understand why it's happening. You run the Polyak step size, and the beginning of the method, the step size is large, goes up, and then reduced by itself down to almost a constant value. And we don't know why this is happening, but that's the behavior that we notice. Okay? And having said that, one can ask now, so I explained what is a Polyak step size, the main format of it, and that it behaves very well for over-parameterized models, these deep neural networks, at least in the experiments that we try and some other people try as well. Now, in terms of theory, one can ask, is there any benefit is only benefits? Do you have a drawback on this method? And we do have drawbacks, and that will be the focus of the next few slides. The most important drawback is that if you don't have non-over-parameterized, if you are in the non-over-parameterized regime, then how you can guarantee that this FSK star is 0? Not all problems have your FI star that I mentioned before, 0. Some of them have, but some of them do not. How we can handle that? And of course, if you care about how high accuracy, how you are able to achieve that. Because I explained the conversions to a ball, but if you are in engineering problem, not necessarily machine learning, but you really care about finding the X star, how you can do that? These are the two drawbacks at the moment of the original SPS. The first, that we need the FI star of FSK star, if you have a mini batch. And the next one, that you can converge to a pretty large neighborhood if you don't have over-parameterized model. And this is what we resolve in the follow-up paper on the Polyak step size that appears in 2 years ago at NeurIPS. And I will quickly go through it because then I will focus on the momentum parts of these methods. So the main contribution here is that we propose a decreasing SPS. So a Polyak step size that, even if it's Polyak step size oriented, can reduce as the algorithm progresses. And by doing that, we are able to guarantee high accuracy solution. Okay. Now, the first fix, and this is what people use these days, is if you go to the original SPS, I explained before that we have this Fi star, which is the infimum of your problem. And I explained that for each loss, least squares, this is equal to 0. And that's the reason that it's reasonable to have it like that. But if you go to any positive function, is not necessarily Fi star equal to 0. So what we prove is that instead of using Fi star, if you know that your problem is positive, you can use any lower bound. Okay. So what this means is you take the Polyak step size exactly as I explained it before, but now we don't have the Fi star. We don't care about it. If you have Fi's that are positive, just using a lower bound of the Fi's is enough. So what this means is that this lower bound is always 0. We don't care about the exact solution of Fi star, the infimum. We care just about the lower bound. And this opens many more problems to use for this kind of ideas. Because if you use a lower bound here, then you just simply have a ratio of your mini-batch over the norm of the gradient. That's enough. And different thing, and this solves the drawback one, the first drawback that I mentioned of how you can know the optimum solution in general problems. That in general problems that are positive, a lower bound is 0, that's okay. And the second problem is, and we have similar convergence guarantees. I will not focus on this, but the main important idea, and this, if you're familiar with AGD, in AGD, what people run is this kind of step size to guarantee convergence to X star. This is a decreasing step size gamma K. You start from X0, and as K increases, your iterations, you just have this over the square root of K in order to go to 0, the step size itself. And the most natural extension is to use this and essentially pre-multiply this thing with the Polyak step size. Will that be useful? And we explain that this leads to divergence. So simply take the Polyak step size and pre-multiply it with 1 over square root of K plus 1, doesn't converge. Okay? And we explain with counter examples why is that the case. And for solving the problem of high accuracy, what we did is that we propose a new step size, what we call DecSPS, that has this format here. Essentially, what you do is you have this CK outside and this CK in the upper bound. And at this point, you don't need to tune the upper bound anymore. You select it to be anything. And this CK is essentially what we have as C before in the denominator. Now we got it outside. And this is the step size that we are suggesting for HGD. And we prove several convergence guarantees for convex and strongly convex problems. And the most important contribution, I will say, is that we will be able to have the first convergence guarantees for HGD that using adaptive step size, and they don't require bounded iterates assumption. Bounded iterates is the standard assumption that methods like Adam and Adagrad require, and is this condition here. I have it, is this one here. So all of the analysis of adaptive methods, what they assume is that if you start from your X0 and you run the method, then you assume that all the points that you will find will belong to a ball of radius d, of diameter d, of the solution that you converge to. But this is quite unreasonable to have, especially in the stochastic case, and especially in unconstrained regimes, that you don't have projections to the convex set. Okay? And this is where we have some convergence guarantees and some theory behind it is for the convex regime. And then we have several experiments in convex setting for this decreasing SPS, where we explain that the highly tuned HGD behaves very similar to the decreasing SPS that doesn't require any tuning. And here the comparison is with the decreasing variance of AGD, just to be fair, because all of them converge. So now this method converges to very high accuracy. There is no ball. If you run the method, you will find the X star eventually. And we compare also with Adam, and all of the behavior is very similar. Adam might not even converge to the exact solution because as a method, it's not using decreasing version of it. You don't care about a high accuracy. You can select the step sizes and the momentum to decrease as well there, but most of the times there is no theory to capture that. In our case, we have an algorithm that comes with theoretical convergence guarantees, and whatever we prove in theory, we just run it. Okay, there is no extra trick on top of it. And that finalizes exactly the SPS and the DecSPS as ideas, okay? And just a takeaway message of this first part before I move to momentum, because it's important to all of us be on the same page of what is presented up to this point. So we explained that the Polyak step-size ideas are useful in the stochastic regime and for tuning the step size of AGD. But then what I should use? Should I use SPS max or DecSPS? And the answer is that if you have non-convex over-parameterized models, just use the SPS max. And we have an efficient implementation of this, just pip install SPS max, that you can run it and you can check in any application that you have if it works or not. There are many non-convex problems and deep neural networks that SPS really works very well. So if you care about them, just try our GitHub repo. Everything is available online. Now, if you have a high accuracy scenario that you really care about, not a ball around the solution, but a high accuracy X star, then we have the implementation of DecSPS available online for you to check it out. The theory holds only for convex problems there. Okay? All of descriptions that I have can extend to non-smooth scenarios. We have the theory, we have the experiments as well. And in industry now, Google has already implemented all of these methods to JAX, the library that they use. And we have ongoing collaboration with Facebook, ServiceNow, and Samsung in different applications that are interested to explore how Polyak step-size can be used in computer vision, large language models, natural language processing, and all of these applications that are interested. And this is related to the two papers that I mentioned, but there are many extensions of the last year. People extend this to stochastic mirror descent, where essentially here we have the dual norm in the denominator. They have second order SPS, they have Newton method stuff, and some extra information related to Hessian. People extend it to proximal scenarios. And at the moment, I'm working on distributed, decentralized setting, minimax scenarios that you can use these ideas to guarantee more robust algorithms, fairness, and all of these that can be expressed as minimax optimization problems. And now I will stop another 2 minutes here before I continue to the last part of the talk. Do you have any questions about whatever I described? The SPS, the SPS max, and the DecSPS. Is it clear when each one could be useful and why could potentially be important in different applications? Yes.
Yeah. I want to know, like, how do you draw the line between over-parameterized and non-over-parameterized regime in your recommendation? Like, what do you mean by over-parameterized? Because usually in theory, it's basically super large width, yes. Right? So in practice, that's almost never happened, right?
So there are settings that people already prove that are over-parameterized. But if you're a practitioner that you don't care if it is or not, and you have a large language model or a huge deep neural network, these are typically close to being over-parameterized. Or they are over-parameterized, but they're not necessarily satisfy the interpolation condition. So in that scenarios, using the SPS max should be your go-to approach. And my suggestion is to just use it with the default parameters that we have, everything default that we have in the GitHub repo. If it doesn't work, then there is only one parameter that you need to tune, is this gamma b, that you will allow to be larger or smaller. But besides that, if it works, it will work well. If it doesn't, it's nothing to be done. There is no theory there to support any of these claims. So I cannot say that it will work great, but in that scenario that you mentioned, I will put it in this category, the first one. So if you have deep neural network, very highly non-convex problem, just run the SPS and see how it will look like.
I'm curious, do you have some kind of results on, like LLMs and so on?
Not in theory. In theory, we have.
No, the theory, like it
in experience, yes, it works. It works. For example, in some of transformers that people use, it works well. In some others, it's really horrible. But there is no really a good way to put it in terms of understanding where it belongs. I will say give it a try. Because people just use Adam W, okay, for this scenario, which is fair, but there is no explanation of why. It's just the default algorithm that everybody uses. So if you see that this Adam W for your particular application might not work great, SPS ideas, just pip install thing and try it. If it works, it might work well. If not, it doesn't. But that's the That's the only part that I can say, because we don't have any theory for this, right? I cannot guarantee that this will behave well.
Right, thanks.
Okay. But I will say it's the same with Adam W. So in Adam W, we use it by default, but we don't know why. Okay.
There's a question online from Siobhan.
Yes.
Would you say that the algorithms you show, example, DecSPS, should also help with generalization?
The DecSPS is only for convex problems and for high accuracy. So we don't have any incentive to understand. There is no generalization there. We didn't try it, and I don't think that this makes sense to try. So the DecSPS is for strongly convex and convex problems, as I mentioned here. If you have deep neural networks, then for generalization performance, the SPX typically have a good performance. Does this answer the question? Let me check.
Theoretically, yes, but you still use them in practice on non-convex problems.
No, we don't. The DecSPS, we never use it in non-convex problems. It's only convex. The SPS is of course in non-convex problems. And we have theory and experiments there. Is that clear, Gemma?
All right, thank you.
Okay, so let me go to the last, yes.
When I'm using Adam W, I use a learning rate schedule. Is SPS going to be sufficiently adaptive that I don't need a learning rate schedule anymore?
That's a good idea. So people at the moment try to use the C that exists in the Polyak step size. You can use a scheduler there instead of C. You can use on top of it. There is no theory, and in some experiments, scheduler help. But from the experiments that we try, there is no reason for using it. I wouldn't claim that this is a schedule-free method because we don't know. But that's a very nice open question for everybody to try, either in experiments or in theory.
Okay, thank you.
Also on that note, you said there's literally one parameter to tune. Is the LAM thing also like a base learning rate, or you literally just pick your
gamma? No, there is nothing. There is no. It's just you go and if you see the expression of the. If you just focus only on this part, you can in the first part of the minimization. Yeah. This is just a function over the norm of the gradient. There is nothing else to tune. Just run this and see if it works. That's it. But the behavior based on the problem. If you plot the step size, it goes crazy. It spikes, it goes down, it fluctuates. There is no any theoretical guarantee of how this will look like. But it goes ups and down. And as I mentioned, we done with the first part just to understand the main ideas. And then this is a paper that we have out a few weeks ago. And essentially, every time that I presented this kind of results, all of the people ask the the same thing. Okay, Adam and Adagrad and Adam W, all of them have momentum by default. You claim that you run SPS without momentum because there is no momentum there in any of the algorithms that I have. There is nothing to tune. So what happens if you add momentum on top of it? That's a question that every time people ask. And that's reasonable, especially practitioners, because any algorithm that you run, SGD, you run it with SGD with momentum. Adam has momentum by default. Here, all the ideas that I presented and the comparisons that I had is with no momentum. SPS is just SGD. And the question is, if you add momentum, and this thing here I have the heavy ball stuff. If you have the heavy ball momentum, will that be useful? That is, use Polyak step size in the gamma k and momentum as a momentum parameter. And this is what we are exploring now. And we have ongoing research direction in this. We have the first paper out, but more ideas will come in the near future. So what we understand now, adding constant momentum, just 0.9 or 0.99 makes the method diverge. So you don't have convergence. Both in theory and in many experiments, this doesn't help. So if you just go and using beta equal to 0.9 and Polyak step size, the method will not converge and will not behave well. So what we did is that we understand this momentum thing using what is known as iterate moving average. And I will explain what this is. And by doing that, we were able to provide two step size selections, the MOM SPS max and the MOM DecSPS, which is exactly the same step size that I explained before, but now in the step size rule, we incorporate the momentum parameter as well, okay? And just to give you the main idea, here is just one experiment showing that as the momentum increases, the method diverges, okay? This is, I'm just talking to the 0.5. If you go 0.9, it just explodes, okay? Doesn't work. So you cannot have convergence guarantees if at least one simple example, convex quadratic or strongly convex, the method diverges. You cannot have that. And what we did is that we take this idea. I will not dive into the details of this algorithm, but the important is the preposition. So there is this method called iterate moving average that has this update rule, which is essentially the SGD. And then you take a convex combination of your current point with the SGD update, and this is your next point. This is what iterate moving average algorithm does. And it's already proved that the iterates of this iterate moving average method are the same with the heavy ball momentum, with the SGD with momentum algorithm that everybody ran in practice. And this happens when you have, in this update rule, the lambda being constant, the beta to be this ratio of lambdas, and the gamma k, the step size selected in that way here. So that's the important thing that we need to understand. There is no reason to focus on what equation 10 and 11 are, but the important thing is that this algorithm has the same iterates produced with SGD with momentum. And now, taking this SGD with momentum, what we suggest now is using this proposition that makes the connection between the iterate moving average and stochastic heavy ball. And now we're producing these two different variants of the step size. So what this says, we have this update rule, okay? With now 0.9 as the momentum parameter. So here we can have the beta being 0.9. Or you can have it to be any constant value between 0 and 1. But what this says is that the step size itself should have this factor here that makes it smaller. So as the momentum increases, a factor that multiplies with the step size should decrease. You can have the beta fluctuate as well, it not necessarily be constant, but if you have acceleration, if you have the momentum parameter, then the step size itself should depend on it. Only then you can have convergence guarantees. Okay, is this idea clear? Before I mention that, look at this update rule. If someone goes and having the beta 0.9 and blindly use the Polyak step size, then the method diverges. If you have the 0.9 here, then you need to pre-multiply the Polyak step size with 0.1, 1 minus the 0.9, okay? This makes the step size and the momentum cone-dependent, and when the one is large, the other is small, and the other way around. When the one is small, the other is large. And there are specific betas that you can use to optimize the performance of the method. I will explain what this means in the next few slides. But is the idea clear? That's the whole idea. If you go and using momentum blindly, the method diverges. If you use it with a beta up here in the step size, then the method converges. And it works very well in practice, as I will show later. Any questions on this? That's the main outcome that I would like just to have in mind. Okay. And here I will just show some convergence guarantees. I will go with I will spend 2-3 minutes on it, and then I will close with some experiments. So the convergence guarantees are very similar to what I explained before for the MOM SPS. So here if you have the MOM SPS max, that is, you run this method here, exactly as you can see it. The only parameter that requires tuning now is the beta, okay? So here the momentum, you need to tune it. Let's say put it 0.99 or 0.9. And now you need to have this beta as well, pre-multiply with the Polyak step size. As I mentioned, C is based on the problem that you have in mind. Here I will just can select it equal to 1 and nothing will be affected, okay? Gamma B is any parameter positive. It can be large. We can have it 10 or 100. We don't care about the convergence guarantees. So the only parameter that requires tuning is the momentum. And we have sublinear convergence, 1 over k, to a neighborhood of the solution again. And then we can do, and here just some comments. This is the first convergence guarantees for an adaptive version of AGD with momentum using Polyak step sizes. And here, the negative side is that theoretically there is no improvement over the no momentum version, theoretically, okay? But this is very typical for stochastic methods. At the moment, we don't know why AGD with momentum is faster than AGD. This is still an open question in general scenarios. So we notice the same thing here. If you add momentum, there is no guarantees that it's faster. And then we have the deterministic variant as well. If some of you care about full batch methods, we have this as special case. There is no restriction there. And we can have exact conversions with a sublinear rate. And we also have the MOM DecSPS, where you can have sublinear conversions to the exact solution now. Similar to what, remember, DecSPS removes the neighborhood. You have conversions to the exact solution. The MOM DecSPS has exactly the same property. And here we don't have any prior knowledge of the momentum parameter. Again, you can tune the beta between 0 and 1. That's the only parameter that requires tuning now, and we try to understand what would be the best choice. But besides that, there is nothing to tune. The method runs by itself. And here we have some, let me close with some experiments just to show the behavior. The AGD with momentum or gradient descent with momentum. In the deterministic setting, we know that there is an optimal version of the algorithm with optimal convergence guarantees. The optimal method is the one proposed by Polyak himself, is the heavy ball method that we know that's optimum for quadratic problems. And the first thing that we wanted to understand is that if our method, without any tuning, this one requires tuning, you require L and mu quantities to be available to you. If we could have a fairly same performance, and this is what we can see, this is our method, is the red one, is not as good as the optimum heavy ball in the deterministic case, but we didn't expect that this will be the case. Our method is fully adaptive, doesn't require any tuning, and still behave in that way. And then we have some stochastic convex problems. Here is logistic regression. And in we can see that the momentum, SPS in that scenario is the best method. And this is why we selected it. It's better than Adam, it's better than Adagrat, and all of these other adaptive methods. And the momentum helps in terms of train loss, is faster, and also helps in terms of generalization performance, train accuracy. We selected this example because SPS, we know that is the best example that shows the benefit of the method, okay? And we also have several other examples. We don't claim that our method is the one that generalizes better than any other method. For example, this here, we focus on CIFAR 100, ResNet 34, and you can see that the behavior of the method is comparable in terms of generalization with Adam, okay? So here you can see, this is a scenario where Adam was better in terms of generalization over SPS, okay? And using momentum, we realize that now SPS ideas are comparable to the Adam set, okay? And let me close with a takeaway message of the momentum variance. Should I use momentum on top of SPS max or DecSPS? The answer is not naively. As I explained, if you just go and have beta equal to 0.9, the method diverges. You cannot have that. You should use this IMA viewpoint that I explained that allows you to have the 1 minus beta in front of the step size as well. And this makes the methods more robust and guarantee convergence. The drawback is that we don't have any improvement over no momentum in theory, okay? But in practice, we notice that using this trick, you can always have faster performance than SPS. Now, next steps, we use now these methods, these ideas with the momentum to see if they generalize as well to more advanced settings, more deep neural networks and rational language models. We already trained several experiments. In some of them, they work well, in some of them are not, and we try to understand why. And the other big question, especially theoretical wise, I explained that everything works when you have beta between 0 and 1. But this requires tuning. Is it possible to have a momentum itself that is adaptive, similar to the Polyak step size that doesn't require any tuning, have momentum as well that is adaptive? And this is something that we are working with, have some results theoretically, and we try to understand how we can make this practical as well. And just to close, that's the momentum part. Just to close, at Hopkins, we have, I'm leading the optimization and machine learning group. And since this is a seminar about introduction to vector, now I start being affiliated with the Vector Institute as a research visitor, and I will be here for the next coming year. So at Hopkins, we have 2 postdocs and 3 PhD students at the moment, and more will join the coming year. And the research of the group is on stochastic optimization, distributed and decentralized algorithms, and algorithmic game theory. And in all of them, we design scalable algorithms, and we try to understand their convergence guarantees and how they work very well in machine learning and data science and engineering problems. And that's it on my end. Thank you very much, and I will be happy to answer any questions.
Any more questions for Nicolas?
Are there any questions online?
We already have discussions during the presentation, so probably it's okay not to have questions, but if you have,
I'll ask.
Okay, go ahead.
Why do I need to choose momentum that's positive? Like what restricts me?
In terms of theory, you can potentially prove that momentum is between -1 and 1. And theory will go through. I didn't see anybody use before anything that is between 0 and -1. So, but in some of our results, the DecSPS the theory only holds for positive momentum. But several AGD with momentum variants and analysis can hold from -1 to 1. But I don't know anybody that uses negative.
in
In
practice.
learning theory,
They do?
yeah.
Okay. Yeah, so it might be the case that if you use negative momentum, you can have benefits in practice. In theory, I have no idea. I am aware of some works on min-max optimization that they use gradient descent ascent with negative momentum to have improvements in theory and in practice. But in general, I'm not aware of negative momentum analysis for AGD that is useful. But that's a nice question. I mean, is if they use it in learning theory.
Yeah, I mean, even like, for example, regularizer, right? So L2 regularization.
Okay.
And there are cases where the penalty parameter is negative, which is optimal.
Okay.
So I think
Yes, at the moment we're using always a positive in the experiment.
yeah, so I'm saying like there are cases that actually negative is the best thing you can do. So I was curious if that also happens in the momentum parameter.
Yes, so I don't think that if you use a very, very negative, I mean, let's say minus 100 will work. But I believe between minus 1 and 1
No, it's
might be reasonable.
so like you can plot the generalization error as a function of the regularizer, and the optimal point could be negative.
Yes,
The
yes.
best, the minimum. I think, I don't know what you should plot here, but maybe.
This is interesting. I mean, we can have this in the proposal, right?
Sure,
Yeah. Any other question? Yeah.
Yeah, I was wondering if you set the momentum, the beta very high, won't the adaptive step size become extremely small?
That's correct. That's the reason that we have, I mean, in terms of still beta between 0 and 1, right? So if you have it 0.99, note that the momentum, the 1 minus beta will be very small. It will be 0.01. But the step size itself is large anyway. This Polyak step size is always larger than the standard 10 minus 3. Or sometimes it fluctuates, but it will not be always very small. You might have a step size itself that is, let's say, 1,000. And the fact that it will have this 0.01, it will just reduce it to standard levels, but it will not be something that is substantially small that doesn't affect the performance.
Okay, but another question. So even if the momentum is very high, there's still an advantage of using the adaptive step size.
I think so. I think so. At the moment, at least with what we have, this is what we see. Yes.
Thank you.
Okay. Thank you very much.
Okay, let's thank Nicolas.
Thank you to everybody online.